materials for water splitting and reactions that are facilitated by charge transfer. So she will go from motion of electrons to modeling dynamics of reactions.
So I based this MATLAB research off of a paper done by Nocera in 2008 where he was working with phosphate and cobalt +2 as an oxygen evolving catalyst. And so what they did is they had put this catalyst on an indium tin oxide plate and then placed it into neutral water and evolved oxygen from that. So that's what I was looking at. So here we can see that we have this reaction barrier that water doesn't want to split. Water's happy as water. And so, so I took these reactant E barrier and E product and put them into the MATLAB code. And to put it into the MATLAB code, I had to put it into atomic units. So that's the conversion up there that I did. And then this table shows some of the ideal values for this reaction. So a momentum of 6 was ideal because once I went above 6, the probability of transfer to oxygen started to decrease. It started to go off, and then I can kind of explain that later. And then the initial position is just where it starts within the wave packet, and then the n tau value of 300. That's just so that it only went one time through the wave packet, so it didn't come back around and start repeating. And then the last thing I had to make sure was changed was the mass. For this particular MATLAB code we were assuming that mass was 1 because we were working with just an electron. But because I'm working with water, we agreed that it should be changed to that value for water. So this is my little video for the ideal conditions. So while that's playing, this is just a 2D representation of what is going on in my video. So what happens is it goes through the wave packet and it comes to the barrier, and some of it gets reflected back, and then some of it goes through and gets transferred into oxygen. For a momentum of 6, we get 90% transfer. It goes quite far to oxygen. And because we were looking at P naught and what the effect is, I went through and I took P naught from 3 to P naught of 6 at 0.3 atomic unit intervals and ran that through the MATLAB code. And these graphs are just showing 2 of them, P naught of 3 and P naught of 4.5, and the n tau values that I had to use to make sure that it only went one time through the wave packet. And as you can see, P naught of 3 barely transfers anything. In fact, if you were to really look at the video for that one, which is on YouTube, it's almost it's really just trapped into that barrier. It doesn't really get transferred. And then for P naught of 4.5, you can see that it increases quite nicely. So based on doing that P naught and running them from 3 to 6, I was able to get some rate information and look at that as a function of the momentum. And as you can see, it increases, as does the probability of transfer for this reaction. And then the last thing that I looked at was making an Arrhenius plot. So this equation is the Hamiltonian that I specifically looked at for this, where V is the potential energy, and because that's kept constant in this, I took the liberty of ignoring that and just focused on this part of the conclusion on the kinetic part of it, and based on that, got my temperatures, and it sort of agrees with Arrhenius. It's not completely linear, but it doesn't have any like large dips and high mountains. So my conclusions: as you increase momentum, you increase the rate, you increase the probability of transfer. If you were to increase the momentum higher than 6, the transfer then decreases, it goes off. And I guess the biggest thing is that this proves that there's some hydrogen-oxygen recombination, so it doesn't want to go to that it doesn't want to go to oxygen evolution, it wants to stay water, so I thought that was a good thing that it proved.
Okay, let's thank Rachel. Okay, any questions? So you did have the parameters of this time step and step in your reaction coordinate. Can you tweak them, and how these parameters affect precision? Can you choose arbitrary values, or?
If you change the values, the precision does change. So it becomes
which is safer? Bigger steps or smaller steps?
Smaller steps are better.
Okay, okay. More questions? If not, thank Rachel once again. So the next presentation by Madhu Babu,